It looks like a slightly different talk than we were giving before. So I have a little bit of a different structure to some of the things that we have already seen, and we go back to, and we then go to deriving the Schwinger-Dyson equation. Okay, so before relativistic quantum mechanics and quantum field theory, we had quantum mechanics, but we need translational, rotational, invariant description, relativistically correct, quantum mechanically correct, and that gave birth to quantum field theories. And we know that all the quantum field theories, which now make the standard model of particle physics, even if you look at a simple atom, you will know what is happening inside the atom, as we know, in fact, is taking into account all these three interactions. Even the parity violating effects are measurable in atomic physics. So we know that when electron talks with the nucleus, its interaction through omega and z, what difference do they make to the spectrum? And of course, then there are quarks and gluons, and the whole thing is placed in a Higgs field, which is giving mass to its particles. Okay. Now, what we will look at what are called the fundamental equations of motion of every quantum field theory. Okay. These equations are important. Their solutions are interesting. The way we can solve them is sometimes controversial and sometimes very insightful, but that's what I'm here to talk about. So fundamental equations of quantum field theory are called Schwinger-Dyson equation. Okay, and they, in principle, encode all the information which is there in a quantum field theory. It is like starting from a Lagrangian and building your equations of motions. You have all the Lagrange equations of motions in classical field theory, and you have Schwinger-Dyson equations, for classical field theory, and you have Schwinger-Dyson equations for every quantum field theory that you study. And this is the S matrix in quantum electrodynamics. This was the article by Dyson a couple of years earlier, written by two famous articles on green functions of quantum fields 1 and 2 by Schwinger, and I think it was Proceedings of the National Academy of Science or something like that, where they were published. And you probably know which one is Dyson and which one is Schwinger. You don't know? This one is Schwinger, this one is Dyson. Okay. Okay. So we know that the fundamental entities in a quantum field theory are field whose fluctuation represent an infinity of particle. For example, this is the scalar field. In field theory, we express it, and that we have creation and destruction of particles. The number of particles is no longer a conserved quantity. We have virtual particles. When we have virtual particles, these are in general off-shell particles. And when they're propagating, we have the propagators of those particles, and we have vertices and all that. And all those green functions which deal with these virtual or off-shell particles form actually the fundamental building blocks of what are these equations, the Schwinger-Dyson equations. Okay. All relativistic quantum field theories, we know the standard models, they admit analysis in perturbation theory. Hadron physics involves QCD, and we know that its perturbative treatment was long known by the initial works of Gross, Pulitzer, Wilczek, and also Tooft and others who probably knew of this perturbative limit of QCD even before them. Okay, so this is where the perturbative limit is. Then if you go to smaller and smaller momenta and larger distances, that means if we are inside a hadron, if it's inside a proton, if we are two quarks, we're very close to each other. That means we are exploring this region. So when the quarks are very close to each other, they don't really talk much to each other. But when they start traversing distances of the length of the hadronic length scale, then they are more and more bound to each other, and they don't out of there. And one of the reasons associated with this is that the coupling between them starts growing. So this part is pretty nice and elegant and beautiful, because perturbation theory is something that you can do it completely reliably and completely systematically. When you do a perturbative expansion of a quantum field theory, you know that every symmetry that is there of the Lagrangian, every limit is automatically obeyed at every level of approximation. There are some problems which can arise by choosing, say, a wrong method to regularize the theory, but that you can always overcome if you know how to fix those problems. Otherwise, perturbation theory is extremely systematic and reliable. But that happens in this and the other direction is relatively more ugly. And we don't know what happens when coupling becomes large. What do? We cannot use perturbation theory. And if we don't use perturbation theory, we are almost at a loss. We have no other idea what to do whatsoever, sort of. Okay, so what are the Schwinger-Dyson equations? Let's generally talk about it first. Non-perturbative QCD is crucial in the study of hadrons. We all know that. In continuum study, that is not when you have space-time discretized, Schwinger-Dyson equations are ideal tool to study hadron physics. Why is it ideal? In my opinion, it is. In many ways are the following reasons. There are, of course, difficulties associated with it. One thing is, of course, correct. These are fundamental equations of motions. The biggest problem is they are infinite set of coupled integral equations among all the green functions of a quantum field theory. Now that is a bit of a problem. If they are infinite in number, then how can you solve infinite number of equations? You cannot do it in finite amount of time if you have to solve infinite, and especially if they are nonlinear coupled integral equations, then it's almost a lost cause. So the structure, as we will see in a few moments, of this infinite tower of Schwinger-Dyson equations is such that the 2-point green functions, which are the propagators. The propagator goes from here, propagator enters, particle goes out. I call it a 2-point green function. They are related to 3-point functions. 3-point functions are the 3-point interactions, like electron photon or quark gluon. And they are related to the 4-point green function. So when you solve one, you know that there is another one. But then there are 5-point function and 6-point function and 7-point functions and 229 time green functions. And they're all related to each other. I'll tell you why there are so many. When I told you that the fundamental interaction, for example, in QED is only electron photon. But in fact, that is not exactly technically the right way to see it. And I'll tell you how it works. So the formal derivation of Schwinger-Dyson equation, which was done by Schwinger, is without any recourse to the smallness or the strength of the interaction involved. Okay, so in fact, that is a good thing, because if it is not, then you can either use it when coupling is small, or you can also use it when the coupling strength is large, as in many regimes of QCD. This is a very good statement. In fact, when people say that we are doing a perturbative expansion, we're doing Feynman rules, in fact, they are studying the same equation, Schwinger-Dyson equation, but in the low coupling regime, where the expansion of these Schwinger-Dyson equation is exactly the Feynman expansion. Okay, so when the coupling is small, these equations do become a Feynman expansion for every green function, whether it's a scattering amplitude or it's a decay through Feynman diagrams. They are, and you can stay at the level of approximation that you want to stay. But on the other hand, if it is not the case, they are still the equations of motions. The only thing is they're harder to solve when it is. Imagine if you were able to solve these equations in an arbitrary scale, then it solves a lot of problems that we now confront in hadron physics laboratories. And in fact, life will become more and more exciting with what is going to be discovered or studied in hadron physics laboratories in the coming years. For example, you might have heard of form factor calculations. How is the form factor of a pion or a proton or a neutron? The thing is that, as I was telling you, that perturbative QCD is valid when the momenta are large. because that is when the coupling is small and you can apply perturbation. So the idea is that imagine if you are probing the proton at a very large scale, which is probing it, okay? Then that is where you can apply your perturbation theory. Okay, so when you become larger and larger scales at q squared, then you can say a q squared is a scale which is probing your proton or your neutron. Then you say, okay, well then I can apply perturbative QCD and get what the result I have. So for example, I can tell you what will be the proton form factor or the pion form factor when this momentum square, which is probing this pion or photon, is large, q squared is large. Okay. That large 10 GeV squared, 20 GeV squared. Now you go to the experiment. For example, if you're looking at the pion, the place where we study pion electromagnetic form factors here at JLab. Okay, so you can do an experiment. When you see the electromagnetic pion form factor, for example, you see an elastic or electromagnetic pion form factor, what you mean is that you hit it with something and elastically and see what it is. Mean elastically that you don't destroy it. It conserves the way it is, but you see how it is. It's an internal distribution of charge or internal distribution of magnetization in case of spin half particles. Now the results which are available with some error bars have been available in the previous experiment before the 12 GeV upgrade, are available at 2.5 till 2.5 GeV squared. Okay, and so the funny thing is that where we can apply perturbative QCD, we don't have experimental results, and where experiments tells us what the result is, we can't use the theory. Okay, that's an interesting thing. And we are talking about pion, which is the simplest bound state that you can ever find of two quarks. So experiment is probing in one direction, theory is probing in another path. So can we do both the things? So when you apply perturbative QCD, so of course you're choosing to go to large Q squared and small coupling. Could we use equations like this and some other method which will be able to tell you independently of the choice of Q squared where you're doing the experiment, where you're doing your calculation, to be able to calculate and then be able to compare it with experiment where the experiment is measuring. And also on the other hand, can we improve our experiments? Can our experiment go to higher energies, but in such a way that still, if you're studying elastic form factors, not break the particles, but it's like something like, you want to hit an apple with a hammer or with an atomic bomb and say, but don't break, because I want to study your elastic properties. I mean, hold on, it's not going to really happen very much. So statistically, there'll be less chance of that happening, but you look for those events in which it is not breaking, but still trying to see it. So those experiments are harder, but with the 12 GeV upgrade and the possible potential upgrade to 20 GeV would allow us to measure these form factors at much larger values. I think 12 GeV upgrade would allow the pion form factor to be measured till about 6 GeV squared or so. But if we output, for 22 GeV upgrade, then hopefully, I don't know if it is for convincing the people who will fund that or not, could go up to 30 GeV squared. Okay, that means that there is hope for next 10, 15 years for the experiment to cover a large momentum region in which QCD we can see in both aspects of it, perturbative and non-perturbative. And at the same time, we should be able to develop our theoretical tools, which should allow us to do the calculations within the same formalism for the large and Q square region, so that we can explore this. And that is when we can see that QCD is working good in all its momentum regions. But the funny thing or thing about QCD is that the fundamental degrees of freedom which make up the Lagrangian of QCD are not the degrees of freedom which we see in the experiment. This is the only theory which we see in experiment are the pions and the protons and the neutrons, but in the Lagrangian we work with quarks and gluons, what we don't see. So what we can see, what we work with, many of those things are not seen, not observable, but from those things, we study quarks and gluons and put them together, and from there we construct observables, and hopefully That's what we'll be seeing. But the next several years, a decade or two, will be very exciting in the sense that you'll be able to do both, I think, experiment and theory in all these regions. And this is one promising place where you can, if you're able to do it consistently, then with the same formalism, you can study the ultraviolet and infrared dynamics of QCD, because it is the same set of equations which give you information of both. But let me just, actually, I shouldn't be doing this because it's all perturbation theory, and we have already seen it, but at least it will set the stage to look at the equations. So this, you remember, this is the Dirac equation for a free field. If it has to interact with a field, we do what is called the minimal substitution, or we do the local gauge transformations, and that is when you have interaction of an electron in the Dirac equation interacting with a photon. One can possibly try to solve this formally, these equations, by defining something like what we can call a green function with this equation of motion. If you do this, then you can say, okay, formally, if I have interactions present, then I can say, oh, this is the formal solution of the Dirac equation. What do you mean this is a formal solution of the Dirac equation? You see, this is the solution when the there's a Dirac particle was a free particle, and this is the new solution psi when the interaction is present. What you say, okay, well, it is more or less easy to verify. What I can do is that operate with this I d slash minus m on both sides, and this is operating upon the variable x, so it is not seeing really the y variable. It's a derivative with respect to x, so it will not be operating upon what is depending upon y, only on this. But I have defined this green function in the way that this is equal to nothing but a delta function. And this is a delta function. This integration fixes a at x and y at x, and this is the solution. And this was the equation which we knew the equation when the potential is present. So this is a formal solution. But this formal solution doesn't seem to help me much, because what you want to solve is for the new field, but that the same new field is also present on the right side. Okay, so for you to know how the field modifies, you have to know the field which has been modified, field which is already modified. So how do I do it? This makes it a bit complicated. So you see that so in part, what is G0 of xy? I would not spend much time on it because I'll come back to it later. So this is something, a green function at x, y, or function of x minus y. And if you take the Fourier transform of it, it is generally what we call the propagator, the Fermion propagator, because you can see that if you operate with ID slash minus m, this does not depend upon x, or y, this depends upon x. So this will operate here, and then it will operate here. It brings you a p slash minus m. So if this S0, you define it as 1 over p slash minus m, then it is the equation. It is the expression for the delta function. Okay, so this is what you have in order to get your delta function. So something like that, the Fourier transform of this thing is what you have as the propagator. I want to propagator that we have seen in our discussion before. So if you can't solve it because you don't know what this is, one of the ways to look at it is, okay, you see here I can insert what was there originally. I can use psi y, and I can use the same expression. So this thing would be this, but evaluated y plus repeated, and this new dummy variable, I'll call them y primes. Okay? So I can substitute here, but it's like postponing the problem to the next step by doing this iterative procedure. So when I do this, it is this plus this plus this. Now what is really happening? It is doing the perturbation theory, which we had seen before, that each time you do this iteration, that you have more and more powers of charge which are coming here in the next step. Okay? Again, this is the same function that we don't know, and we can do another iteration, and then you can go to the next step. I don't know if I've shown it here or not. Yeah, I think it was just it was a fun way of keep doing it. So that is happening. So you do an iterative procedure, but that is perturbative because you can do it infinite times that you want. But at each step, there are new powers of E which are present. It's E squared here, E cubed here, and that will be E4. And if you have the small charge, you can always say, okay, then if charge is a very small quantity, then E squared will be much smaller than E4. Okay, so I can stop there, and next I will only go when my experiment is sufficiently smart to do a precise measurement. And if I need to compare with experiment at higher precision, then I can do a higher order calculation and go closer. But that is again, it's at the heart of perturbation theory. And of course, if you say that your E is not a small quantity, then it really doesn't matter. No new step of iteration is going to be smaller than the previous one if E is equal to 1 or 1.2. And therefore, you have to do a calculation of these infinite diagrams, and you don't have time because you have a finite time for doing your PhDs. And okay, so the same thing happened with the green functions. You see, imagine you have the green function equation, and then if it is your propagator, that is the Fourier transform of this green function is present in an external field, then you can do the same thing. You have an initial green function, and then you can keep applying this iterative procedure, and you will know this green function at every order of accuracy that you want to do. But we want to rather look at it in the momentum space. We know what G0 was, which was this one, and see what it will look like if we do some perturbative expansions. Okay, so this is the type of argument which Dyson started looking at and see where we can get it. So this is imagine this is present then in an external in a potential in an electromagnetic field, or this is a propagator. It's a virtual particle, so that it can emit or absorb virtual particles all the time. So this propagator, this is a one-loop self-energy correction that we were talking about calculating today. So it can emit a photon and it can reabsorb it. It can do it once, it can do it second time. Okay, it can do it many times as it wants. Or there are a particular type of diagrams which we call the rainbow diagrams. Okay, it means that it it emits one photon, then it emits another one, absorb this one, then absorb this one, and this, it's all series of diagrams. And then there are other series of diagram which looks a bit like this. This is where this is photon self-energy is present. And then in photon self-energy, you can have this, photon being exchanged here. Then you can also have this photon splitting up into a quark electron positron pair. And then so many things can happen, infinite things can happen in this. And then there are diagrams like this one, in which it appears like, you emitted, but before you absorb your photon that you emitted, you first emit another one, then absorb the first one, and then absorb the second one. So when you look at, keep looking at, this is possibly all diagrams in QED that you can see, all series of diagrams. You can make any combination, it will fit into one scheme or the other scheme. So that is what Dyson could manage to observe was that all these diagrams, which we now call the rainbow diagrams, in fact, can be summed up. Let me see if I can. I think I have. Sorry, if I can do this. All these diagrams which are here in such way that you can, I can make a circle here, and then I squeeze the circle. And then I can make it smaller and smaller, and it becomes, I can absorb it inside this blob. I can do the same thing with these one and all this. What I want to say is that all these rainbow type diagrams can be put together, and they're all like, can be considered as a correction to this propagator here, because they're not disturbing this photon or this vertex. It's not talking to these ones. And all these corrections, I can put further blobs, I can put blobs here, and all this are the type of diagrams which in fact are modifying my photon propagator. So this blob is for the photon. And all these diagrams here, this kind of diagrams is another, which is in fact can be considered a correction to the vertex. Okay, because these I cannot put them in the form of, in this form or this form. So this is, and then because I can do it repeatedly, so once it is done, all the thing can be repeated here, and this is the whole thing that can come here. The thing that probably cannot come here and shouldn't come here is the following. And that is, okay, look at this diagram, okay? If with this diagram, what I could do was that I could have made this photon a bit smaller in size and this one a bit bigger. And then I do an upside, you know, if I'm holding all these sticks and everything, I make a 180 rotation, and it can look like this. So basically, you cannot have another blob coming here because it is actually the same thing which was here, and it's not, you know, how do you say, topologically different diagram. So if you put a blob here and a blob here, you know, you're double counting the diagrams. So the blob here is the same thing as blob here or there. So you can put them together, and all of this thing is actually this one single equation that you can name, what you can call this, that this is what is your full fermion propagator, and this is your full fermion photon vertex, and this is your full photon propagator, and then back again, this is your full fermion propagator. Now, you can say, oh, hold on. What we did was a perturbative expansion, and then you're summing up the series. But you could derive this thing formally from path integral formulation without ever having to do the derivation, just defining your propagators, complete propagators in the presence of a quantum field theory. Now here, this thing with the blob which is there, I could actually start expanding it again, and it will be just repeating the same story. Okay. Now this thing is called self-energy, but for the fermion, the way it is defined here, this is of course not the self-energy at the one loop level. It could be written at one loop level if I just replace this by the bare photon propagator, and this by the bare, and this by the bare. This will be one loop. Okay, but in principle, this is not one loop self-energy. It is the full self-energy. So what I can write is this equation symbolically, if I have to write it. And this is the full fermion propagator. So this is the bare propagator. Then it is plus this piece, the bare propagator. Then there is this self-energy. Then this is the bare propagator. Now it is the bare propagator, the self-energy, another bare propagator, self-energy, bare propagator, and it continues. Now again, as we were seeing in the last lecture, what we see is that these two terms are actually common to everything which comes after the second terms onward. So we could take this S0p times sigma as common, and put a bracket here, and then this expansion is actually the same expansion which was there to start with. Okay. So this thing, what we have is nothing but the full fermion propagator, and therefore all this summation I can write it as full fermion propagator equal to bare propagator plus bare propagator, the full self-energy multiplied by the propagator again. Okay. So this is the equation that I have. Now I can do is that multiply again from the right by S inverse of P, and from the left by S0 inverse of P. So for example, this thing, this with this will give me 1, and this will be S0 inverse of P, this will be N inverse of P, and this simply will disappear, these propagators which were on the side. And therefore, for the inverse fermion propagator, I get this equation in which there are no propagators there on the sides anymore. Okay. So this is what is called the Schwinger-Dyson equations for the electron propagator. Dyson, of course, derived it this way, putting the diagrams together and doing the derivation, but there is a non-perturbative derivation of this. The only thing is you have absolutely no idea of what these quantities are, these full quantities. If you had done it for QCD, you would arrive at a very similar equation for the quark propagator. So the same equation, instead of a photon here, there's a gluon. That's the only simple diagram I can show to you, because there's no other diagram in QCD which is as simple as in QED. We'll see it tomorrow, I think, in the first or the second. So this is what happens. If you start looking at these equations, you can see that you can derive all of them. So this is the equation for the electron propagator, as I've shown you. This is the equation you will derive for the photon propagator. Of course, when there are fermion loops present, you can always, put a number of flavors here. So you can see that the different fermion. Then there is an equation for the vertex as well. And this is where I wanted to, maybe your attention is that it's the bare vertex plus it here, there are propagators involved. This is the same propagator for which the equation is here. And then there is this is called 4-point green function. But you say, but there is no 4-point interaction in QED. But see that, okay, there is no 4-point interaction, but it's a full blob. And the first term which starts here is actually not a point interaction, but a photon being exchanged. Okay, so this is, as you can see, is that this blob is something like, it will start, this is the first terminate expansion, it goes on like that. And there are many things. So it's something like a scattering of two particles. But this is a full, because we don't know if we can do the perturbative expansion or not. This is something, a 2-point function, a 4-point function, which could be non-perturbative. Okay, and then you can derive this, another equation, and that will be related to a 5-point function, which is like, I don't know, 3 particles scattering to 2 particles or something like that. And then 3 particles going to 3 particles. It never ends. So you can see the way its structure is that this is the equation for the 2-point function. And in this equation, you have to know a 3-point function. Here there is a 3-point function, and it has an OR equation, and it is related to a 4-point function. And when you will have a 4-point function, it will have its own Schwinger-Dyson equation, which will relate it to a 5-point function. And say, oh, this is not looking good. Okay, the only thing I can do, and what we do in perturbation theory, is that if we are going to solve for a 4-point function, we do a simply scattering amplitude, do it at lowest order, and at tree level, and then we go to higher level and to the level that we want. But we don't want to do it this way. Okay. So let me see. I don't remember actually where I was going, so I had to see this. So let's look at this equation, and let's try to butcher it a bit and see what do we find. So if I try to write this mathematically, this equation, so this is like the inverse propagator, the full propagator, which has all the infinite corrections in it. And in fact, I shouldn't say infinite corrections, because when you say infinite corrections, I already have in mind perturbation theory. Okay, so I don't have the perturbation theory in mind. So I'll just call it a full propagator. And then you have there the bare vertex, the full propagator, the full vertex, and you have the full photon propagator, because we are looking at QED. Now, what you have to know is that instead of this electron, it could have been a quark as well, because we know that quarks also have electromagnetic charge. So there is a QED for quarks. And that becomes, in part, very important, especially, for example, this form factor calculations of the pion, or pion making transition to something else, especially in electron-proton experiments that are carried out, because what really goes inside to see a pion is a photon. Okay, although the structure of pion is determined by the strong interactions, but we observe it by throwing an electron onto it, which emits a photon, and photon looks at the quark, which is a charged particle. Okay, and the interaction is electromagnetically charged. So all the 3-dimensional structure that we want to find out is basically through the electromagnetic interaction. So these interactions, electromagnetic interactions, you will see in some of the calculations, are extremely important, especially for the normalization of the elastic form factor. Now, this is the bare propagator, but when you say, what do we know about the full fermion propagator? What can we possibly know about the full fermion propagator? Okay, there are 2 things that we know, is that it can only depend upon one momentum variable, because this is just one electron with a certain momentum, virtual particle. How full or not it is, so it depends upon one. And it's a Dirac particle. When it's a Dirac particle, it can be expressed in terms of Dirac gamma matrices. If it were a scalar particle, we don't have gamma matrices, so it doesn't have those. If it is a spin 1 particles, then we will have more Lorentz indices available, like G mu nu, what we have for the photon, but we don't have it there. Okay, we don't have any Lorentz index. So the liberty that we have for the fermion, one fermion, only allows it. Its most general expression you can have is it can either be proportional to a p slash, like a p mu and a gamma mu, because it has to be contracted, because I know that propagator doesn't have any index, or simply proportional to a unit matrix. Okay, and that is actually very similar to what we have here. If you look at an S inverse, it is p slash minus m, nothing else. Okay, so one part which is proportional to p slash, one proportional to a unit matrix. And here it is the same thing. So you can either write it this way or write it this way. If we write it this way, it becomes very similar to in structure for what we know as a Baire. So that's why we use the symbol m for this, because eventually we can say that when it is Baire, it's the same thing as the mass of the particle. And when it is not, it's something different, but let's still call it m. And we can call it m function, mass function, or something like that. But whether we write it this way or this way, it doesn't really matter, because these are equivalent to each other. And we can see this, no? If we write it as such, I mean, it's a bit strange to write matrix, as you know, in the denominator. So what we do is multiply on the top and bottom with this, and then you expand this out, and this thing is nothing but p squared minus m squared, and this is a scalar thing, and when you know this, it comes with p slash and with this, and then there is another term which is this. So I can identify all of this as b of p squared and identify all of this as a of p squared, and you can see that this is really equivalent way of writing this propagator, the whole thing. Okay. And then we have this photon propagator. Okay. Now I had told you that QED is something very, very special. In what way it is special is that this is the total structure, this is the transfer structure, and this. And transfer is, of course, that because it is transfers to the photon momentum. What happens is that the full photon propagator can only be expressed of one unknown function that we don't know, because we have already shown you that this part never gets modified through Ward identities. Ward identities protect the longitudinal particle and longitudinal part, and I have already told you that Ward identities are non-perturbative in nature. So perturbatively or non-perturbatively, this is never going to get modified. Okay, in QED. This gets modified at higher orders, and higher order will be different. The only interesting thing is that this will never depend upon the gauge of the in which we are working. You can ask me, but I'll not answer you why. I'll answer you eventually, maybe in one of the lectures, but not now. So it can, but all the corrections to the photon propagator come through this number, which is number of flavors. Okay. Now again, you have to live with me for a little while, not for long. That this NF, you can also treat it as a mathematical entity, mathematical number. Okay. And I say that, look, theory is not going to change if m is 5 or 4 or 3 or 2 or 1 or 0. Well, when I say 0, it means that there are no fermions, because there is no flavor I'm talking about. But mathematically speaking, the structure of this is not going to change much. And I can assure in many of the properties, like for example, when we calculate any theory to calculate the masses of the hadrons, masses of the baryons, for example, if you work in this approximation, which is called the quenched approximation, in which you don't have the loops, the result is, not different from the result within 5 to 10%. Okay, so this approximation is not that bad, but I want to do some approximations, because if I don't do that, but I can't solve that. I can't talk to you much about the solutions. So I will work in this, what is called the quenched approximation, in which I take this as a mathematical entity and saying nothing else. Okay, but then you say that this is a big approximation. We will undo it eventually. But one of the first thing is, we have just seen in the previous lecture that the only thing which makes the coupling run in quantum electrodynamics is this diagram. because Z1F, because the fermion and the electron ones cancel with each other. And this is the only diagram which renormalizes the coupling. And if I make this approximation that this is 0, it means I'm not allowing my coupling to run. Now coupling is frozen to one value, whatever it will be, because there is no renormalization constant involved anymore. Okay. I know that you're feeling a bit surprised, but we will come back to it. Now there is another thing that I have to do, but probably I'll go. Well, how much time do we have? I don't know. Yeah, I can go on, she says. So that's good. These are infinite equations, so probably I need infinity of time to make them clear. There's another bad thing I'm going to do it here. I tried to convince you wholeheartedly in the first lecture that use the dimensional regularization because other things are bad. And now I'm going to be a bad boy. And I'm not going to use the dimensional regularization because I don't know how to do it. I know how to do it, but in the simplest of cases, and where I did it, and it worked well, and I said, okay, that's fine. It's only one paper I ever wrote on that. The thing is that when I will introduce here eventually a cutoff scheme, a hard cutoff to solve these equations. Although I'm still, working with DDK. But when you put a hard cutoff, usually in your perturbative calculations, you can lose translational invariance that I had mentioned explicitly. When there are gauge theories involved, you can also lose the gauge invariance. Okay, so this is a bad approximation to use. So one of the consequences of gauge invariance is these watered entities. And what from experience we know in the field is that there is one thing you can try to do is the bad thing that it does, you can undo it by using a simple trick. And the trick is the following. You divide your photon propagator into two parts, the longitudinal and the transverse. So this is the transverse part, which will get multiplied with the rest of the equation. And here you have a Q nu sitting here, which will multiply with this full vertex, whatever it is. But before you use the cutoff or anything, what you use is you use your watered entity here. And that will ensure that your gauge invariance will not be violated for the translator. This is the trick that you learn with time. Okay, you do it, and I will tell you later how you find out that it works well. But you have to use it at this step. You don't delay it any further. So you use it, and because it allows you to do the following thing. You see, if you get two parts. This S inverse of K, which lies here, which cancel with this S of K, which will give you unity. Now, this thing is important because this, as we know in dimensional regularization, it is 0. It is explicitly 0. And when you use the cutoff method, before using it, and if it is not 0, because you have put a cutoff and it's no longer going to be 0, that messes up the watered entities. So you use this, you use it's an odd integral, that's why it is 0. So you put this equal to 0, and then you will see that if you had used the dimensional regularization or the cutoff, you end up getting the same results for different calculations that we were engaged in doing it. So you have to use this trick. So, so what is it that we haven't done here? Let me see. Okay, another thing what we were going to do here, and we will undo all these things tomorrow. I will use, instead of the full vertex, the bare vertex, which was there just in perturbation theory. Okay, as I have told you that when you do non-perturbative physics, this is not gamma mu. It is a huge long expression which contains 12 basis vectors, and we have no idea of the coefficients of each of them. Okay? And that's what we will do tomorrow. Tomorrow will be, I think, a bit more technical, and if you don't want to pay a lot of attention, you don't need to, but the final results will be interesting. So I have taken it all. So it's basically perturbative. I have used perturbation theory here. Just I've taken the bare propagator, the bare vertex. The only thing I haven't done is that I haven't put the bare fermion propagator here. Why did I do this? Because if I do this, this equation gets decoupled from all the rest of the infinite set of equations, because I don't need to know the full photon propagator. I don't need to do the full vertex. what I need to do is on the right side, and also what I need to do is on the left side. If I could somehow solve this equation, then I will find the solution. How do I solve this equation? I don't know yet. So this is the full Fermion propagator here, but this is the function of the momentum variable, which is the loop integral. And it's also here, but the final results is again that. Okay? So that's a bit of a tricky equation. There is a type of equations that call you what type of equation these are. This is the simplest kernel you can find, and you can only make your life worse. You could do it in perturbation theory as we did. Write this as S as 1 plus something, or the bare plus something, and calculate in perturbation theory, but that's not what you want to do. So what you do is that on the right side, you put the full form of the equation, which is like f of k squared divided by k slash minus m of k, and you put S inverse of p, which is p slash minus m of p divided by f of p, the general form that we had written for the Fermion propagator. On the right side, left side, you put them everywhere you find, and you find some equation that you still don't know what to do with it. Okay? One thing you have to know that this is basically a matrix equation, because these are matrices here, p mu, gamma mu. In fact, these are 4 by 4 matrices. So in fact, yes. Yeah, this Q is K minus P. Okay, yeah, I probably didn't mention it previously. Its Q is K minus P. This is the momentum of the photon. Yeah. So yeah, so it depends. It's yeah. So it's K is the momentum variable, and this is K minus P. So if you're able to do, then you're only left with P on the left side. So these are in fact 16 equations in this matrix equation, because it's a 4 by 4 matrices on the left and right. The only good thing is that you can try to see all these 16 equations, and you'll find it, then only 2 of them are independent of each other. Okay. And all the rest are just multiplication of one with, with something to get this other one. Those are not independent. And you can decouple those 2 set of equations by doing the following trick. You multiply this whole equation, say, by p slash, and take the trace of the equation. What happens here, when you take the multiplied by p slash, this left-hand side becomes p squared, p slash is p squared, and this becomes p slash. And when you take the trace of a number is 4, yeah, and the trace of one gamma matrix is 0. Okay, so this will become 0, and this will become 1, or 1 over f of p squared, or p squared over f of p squared. Or you take the trace of this equation without multiplying by anything. So this trace of p slash will be 0 of this term, because this is one gamma matrix and there is no gamma matrix. So this will survive and this will drop out. And that's all you can do. You could do all combinations and taking traces, and you will end up either with one equation or the other equation. There is no more equation, no further equation to it. So either you have this equation, this is the first you get after multiplying by p slash and taking the trace, or the second one. Now here, I will let you do all this math. I'll just tell you again what are the trace theorems. You do all this to simplify this, and then you do the angular integration in d-dimensional solid angle, and then do all kind of stuff. And then what you do is that also you do the calculation in Euclidean space. People can also do it in Minkowski space. Just it becomes a lot harder. But or you do that in the space like momenta. What you do is just you rotate it into the Euclidean space, and this is minus pe squared, which is different from the Minkowski space p squared. But then I have to do it. I have to put a subscript pe in every calculation. But once I have rotated it, then to make the notation simple, I will simply call wherever it is ke, I call it k, because now the Minkowski thing doesn't exist. So I don't want to make my life complicated. But now the momenta are all in Euclidean space. Then I do all the I'm still working with one equation. I'm doing several simplifying tricks that you can do to see how far I can go. Then I'm in this Euclidean space. I can have this solid angle defined in this 4 space. And if you do is your d4k is written in terms of this radial variable, and then there are angular variables. Okay. And then you make a choice of the external variable in certain direction, which is completely without loss of generality. And in the end, what will happen is to do the angular integrations, because your m and f do not depend upon any angle. They only depend upon k squared, but not on the angle between k and p, because there was no dependence of m or f unknown functions on q squared, which takes the angle between k and p. Q is k minus p, it is k squared plus p squared minus 2 k dot p, and that is knows of the angle between k and p. So the angular integration can be done, and there are different angular integrations that you will need. I'll probably give you, I have a manual in which you can do it. There is a PhD thesis one somebody had written, and then these are the, I think that was me. So no, it was someone before me who had done it. So and I just added a few one afterwards. That all the things that you need is, it tells you how many denominators you have of k squared or p squared below, or q squared below, and then you keep doing it. And this theta function only tells you that when p squared is bigger than q squared, then this is the one survives and this is the one goes away. And you do all this angular integration, and then you finally arrive at this simpler expression for one of the two equations that we have. You can just try to imagine how things will become complicated when you go to very complicated kernels. And this is the simplest example, like the potential with the infinitely long charge that we will be doing. So this example, I'll try to go through all of this. And then you do the same thing for the other function, which is called the mass function. Okay? The mass function, because if we were in perturbation theory, it will just be the mass which appears in the propagator, small m. Now, when you reach this point, there will be another approximation. Not approximation, we'll work with a choice of gauge. Okay? There is a gauge parameter here. But the funny thing is that you can see here, this gauge parameter, if you had just taken it to be equal to 0, this xc, this will make life so easy, because this term will drop out, this term will drop out, and f will be just equal to 1. Okay? And here there will be, all these things will disappear. So f will become equal to 1. You can choose to work in the Landau gauge. We will also undo this approximation by tomorrow. Okay? But tomorrow, yeah, afternoon, for first lecture, we will undo this equation. So bear with me today. So this becomes simple, and in fact, in the end, you have just one function, which we can call the mass function, but this is appeared on the left side. It also appears on the right side. I can't do much. So this is the unknown function. This is the unknown function. To know for the unknown function, you have to know the unknown function. So that's a bit complicated. But there is one thing which can be formally done. There is something called bifurcation analysis. I will come back to trying to tell you what it means officially. It's the following. What we are trying to look for is something. Remember, we had this propagator at the tree level, which is p/minus m. Okay? I'm going to put this m equal to 0. Okay? That I'm starting with a Lagrangian where there is no fermion mass. Okay? And what I'm going to try to see eventually, if I drop this m and put m equal to 0, can there still be a solution of this? You see, if I put m equal to 0, one of the solution is that m equal to 0, this big M. If I put this equal to 0, this is 0, and the equation is solved. This is the solution that we see in perturbation theory. If you could do a perturbation theory to all orders, then you will see that if your mass is 0 in the Lagrangian, at all orders in perturbation theory, your correction to the mass will be proportional to the bare mass. And if that is 0, all your corrections will always be 0. So there is no non-trivial solution tenable in perturbation theory for the mass if the original mass in the Lagrangian was 0. Okay? What we want to try to see is what happens if I put m equal to 0, can I still get a non-trivial solution for this mass function? One of the ways to see it different from perturbation theory is something called bifurcation analysis. This is formally correct in mathematics, in which you have a function with this form. You take a functional derivative of the equation with respect to this m function and evaluate it for m equal to 0. Okay, and that is which will tell if bifurcates from a trivial solution or not. Okay, I can't go into that, but the upshot of this is that if you apply that bifurcation analysis, it is equivalent to saying is that I'm dropping all terms which are proportional to m square or m cube or m higher power, because they always drop out when you take the derivative and then put m equal to 0. You can see that. So I do the bifurcation analysis, and I want to see if there is some solution which bifurcates away from the perturbative solution. Okay? Now, this is a slightly bad thing to do, actually, quite bad thing, and I'll tell you how it is bad. One thing is that obviously you can see that this is a trivial solution, that m equal to 0, a trivial solution. I'm looking for the non-trivial solution. Now look at this solution. You see, in the original solution, if I had put m equal to 0, and if I hadn't applied the bifurcation analysis, there is an m squared sitting there. Now there is no m squared sitting there. But that causes a bit of a problem, because when you go to k squared going to 0, this has a lot of, a lot of contribution coming for it. So even you can see that, k squared going to 0 limit is giving you a contribution which was protected by this m squared, which was here. So you can't really drop this and try to find the solution in m squared going to 0 region. All this I'm going to do numerically. I'm trying to find if I can do an analytical solution which you can understand yourself. And then I'll do it without any bifurcation analysis, without any gauge fixing, etc. So what you try to do is the following. There are two things here. Wigner mode solution is what we call it the perturbation theory solution, that if M0 solution. Nambu solution is the non-trivial solution which we found with Nambu-Journal-Licinio model. That there was no scale invariance in this equation for m equal to 0 because of this m squared. But now I have introduced by this bifurcation analysis a scale invariance. So I multiplied with any number. It's the same thing before because m only comes here. And there is a lot of contribution to this, and that's no good. So I have to introduce a cutoff, because this is introducing in this region from 0 to epsilon squared a contribution which was not there in the original equation. This was not correct. So I will not go down to 0. I will say I only go down to say m squared, because that was what was protecting it. When k squared is 0, it only goes down up till m squared. So I will say I will introduce kappa squared in the infrared, and which will be the order of this m squared, so that I'm not cutting off that contribution which I'm trivially introducing by making this analysis. So I have this kappa squared introduced, and this is the equation. At all time, you can see that one of the solution is the perturbative solution. Right? Now I introduce p squared equal to x, k squared equal to y, and write this equation as such. So one of the things that I can do with this equation is convert it into a differential equation and then try to solve it. Okay. Now, how do I do it? Just take the derivative of this. Now, you know that if you take the derivative of this term, there are two terms which depend upon x. One, this function, because this limit is x. And secondly, this one, which is x. And this depends on x here. So when you take the derivative here, once I take the derivative of this will be minus 1 over x squared, and that is what comes here. Okay? When I take the derivative of this, what happens? It only looks at the integrand, and where y is replaced by x. And here, it also does the same thing, but this at x has a different sign from this, and therefore those terms cancel from taking the derivative. Okay? And the only term which lives on is this term. Huh? This also imposes a boundary condition we call infrared boundary condition, because if I put x equal to kappa squared, the integration will be from kappa squared to kappa squared, and that is 0. Therefore, when you integrate once, you have to put a boundary condition. And this is the boundary condition which is there, the derivative of m at k kappa square equal to 0. Okay? So something like this. If there is a mass function involved, in the infrared region, it should have a plateau because its slope is 0. Okay? So this is something like giving you a hint of where you will eventually go. You probably know that more or less. Okay. So let us write down the first derivative as such. We have this x squared. I take it x squared to the other side, and I write it this, and take the derivative again. So I take the derivative again, that it's a second order differential equation, x squared m double prime, and then it is 2x here, m prime x, and here only the top part stays, and this is 3 alpha over 4 pi mx, and I bring it to the left side, and it's just a differential equation of the second order. Okay, now I go back a little bit, and the reason I want to go back is a little bit is the following. Remember, our original equation was this, where x was on the left side. The reason I want to write it again is because I need another boundary condition. So I want to see what is the other boundary condition which is reasonable and I can use it. So I write it like this, and then I take the derivative of this equation, and only this term, only one of these terms survive in this, because the other two terms go to 0. And this picks out the ultraviolet condition, because if I put x equal to lambda square, then this thing goes to 0, and therefore there is a boundary condition on the ultraviolet, there is a boundary condition in the infrared, so the integral equation gets converted into a second order differential equation with two boundary conditions in the infrared and in the ultraviolet. Now what you will find out, and this is also what you can prove formally for such equation, is that this is a solution, what is called the multiplicatively renormalizable solution, and that is what it has a significance, I'll come to it, that this equation has a solution which is x to the power minus s, which is not the solution of perturbation theory, which is m equal to 0. So you, in fact, can do that. I will ask you to do it. Can you tell me if you find the solution now? Imagine if you put mx equal to x power minus s. Okay? So here there are two derivatives involved. So eventually, when you write it, there will be an x power minus s, which you can factorize out. And first derivative or single derivative here, it will give you s times s plus 1. It will give you s, and eventually it will become a quadratic equation in s. Okay? It will become a quadratic equation in s, and you can solve it. And this quadratic equation is this. This is the coupling which is there, e squared over 4 pi, and the coupling is frozen because we are not allowing it to run. And there is a number pi over 3 which comes here. And we call it alpha c, this number pi over 3. And these are the two solutions. It's a quadratic equation, half plus minus half, 1 minus alpha over alpha c. Now you will see one thing that if alpha was equal to alpha c, one of the solutions is that this power disappears completely. Okay? But then if alpha was different from alpha c, then there will be a complex solution which will arise for alpha greater than alpha c. What is interesting to see is that this number is differentiating between two boundaries. Below this, there is one solution, and above that, there is another solution. Okay? What we will eventually find is that below this number, we only see the perturbative solutions. And above that number, we see a non-perturbative solution where the mass function can become complex. Okay. What is interesting to find is that what is this number pi over 3? It's around the order of 1. That's where we expect the non-perturbative physics to set in, because the coupling is no longer small. Right? So this is only getting the hints of where eventually we want to go. And this is a solution only, doing it analytically, but we will do it numerically without doing any linearization, without doing anything else eventually. Final solution we will see tomorrow. So this critical coupling corresponds to the boundary of a phase transition where real and complex solution bifurcate away from each other. And you can write this solution, but then of course you want to use your boundary conditions, which will fix what is C1 and C2. And that's another equation, because C1 and C2 eventually themselves will be complex numbers. And once you do this and solve it near x equal to 0, where where x was small, where we introduced this kappa. Remember, we put a kappa, which was the infrared regulator that we put, and kappa was the order of the mass m of k at that point. So if we solve this, put this boundary condition, we found that there is this solution, and kappa was really not different from, it was the mass at the value kappa. Okay. The boundary condition that would kappa square was m square of the order of m square of k square. So this is what is a solution, which is non-perturbative. This is k is proportional to lambda, and then there is this law, which is actually a very well-known law in various condensed matter theories and other theories, which is called the Miransky scaling law. Okay, and I will tell you later what this Miransky scaling law is. And then this was nothing but we had put this infrared cutoff. There are many ways of putting this infrared cutoff. And if you want to numerically solve it, which you have to use through computer, you don't need to do that as well. So we will come back to it eventually for the numerical solutions. So this is the solution. This m of kappa square is this. And when you go back to this solution, okay. I'll come back to this solution in a little while, what this solution indicates. It's just this solution which is not finding perturbation. What I want to tell you here is that it doesn't matter how much you complicate your kernel, if you want the full vertex, the full foreign propagator, this mass function will eventually always have a form of this kind of equation, integral equation. These are called nonlinear Fredholm equations of the second kind, when this kappa will depend upon this x and this y, and these can be complicated functions, and then you can solve these equations. When these are complicated kernels, this can be extremely complicated kernels, which can have, actually you can be solving for 12, 20 functions simultaneously, all connected to each other, coupled, but you're stubborn and you're not using perturbation theory, okay? And that's what we will try to do is, if we had done the solution numerically, what you find is the following. This is what we have drawn here is the mass function m of p squared as a function of p, numerically solving without any, how do you say, linearization or anything, divided by lambda, because we have regularized the theory, we have not renormalized it. So what we draw is m divided by lambda. We find that there is a mass function which goes flat, which we had already seen. One of the boundary condition tells us that the slope of this function in the infrared should be 0. And that tells us that it should be a flat function in the beginning. And then it drops. And eventually we'll see that it drops off as a power law. Okay? And that power law is very similar to the photon propagator in the power law, in the perturbation theory. Okay? But I'll come back to it later. Then I start reducing this value of alpha. When I start reducing it, you see that the solution becomes drastically reduced. And I keep reducing it, keep reducing it. Of course, I don't have the skills to do it with this accuracy and this. I can't go below this. And this is the number when it is approximately pi over 3, this value. Okay? Because when I hit pi over 3, the only solution I find is 0, no other solution. So this flat solution decaying is the only solution which I find above the value pi over 3. And if I draw it, if I draw the numerical solution on top of this analytical solution that we had found, this becomes like this. This was numerical solutions are these dots, and this red line was the analytical solution. It's pretty cool. But it tells you that from here to here, this generated mass is always 0, from 0 to pi over 3. When you go beyond that, you can either have the 0 mass, or you can have a mass different from this. But it only gets generated when your coupling is large. And there is something like that we will find in QCD that happens. In QED, it doesn't happen. But if we were living in a QED with a coupling which was not 1/137, but which was of the order of 1, then we'll find that in QED that will happen is, again, that you can have chiral symmetry breaking and the masses can be generated even if there were no masses in the Lagrangian originally. Okay, that's where I will stop and try to think that, we did a lot of butchering of these equations. Can we go further? One thing funny that you will find, and it is correct, is that fermion masses are strange things, the quark masses or something. Whenever there is a mass scale available to them, they always develop masses proportional to that mass scale which is available in the problem. What happens in QCD? You see that in QCD, the interaction is strong and it generates a mass scale which is called lambda QCD, which many people knew. And your fermions have masses, and those are proportional, and those are dependent upon this lambda QCD. In QED, the mass scale we put was ultraviolet cutoff. And we saw that m over lambda, they start depending upon this lambda. And it also, of course, depends upon the value of the coupling, but lambda. In QCD, there is lambda QCD available, and you see the fermion masses, quark masses will be. You can study QCD phase diagram in the presence of finite temperature and finite chemical potential, and you will see that for quark masses will depend upon what is the temperature of the medium, what is the density of the medium, because they provide you the mass scale. You can put your quarks in the presence of a magnetic field, and you solve the equation, you'll see that they will depend upon the square root of EB, which is the mass scale available. So whatever mass scale you give them, they develop masses, and they start developing on that. But then there will be a controlling parameter which can determine if that mass can be generated or that can not be generated. This is an example I had used to once study condensed matter system, the system of graphene or system of superconductors, in which you study QED in 2+1 dimensions because you're only in one plane. And you know that when you change the dimensions, we all know that your coupling can have dimensions because the coupling in 4 dimensions is dimensionless, but coupling in other dimensions can have dimension. If you're in 2+1 dimensional world, your coupling parameter alpha is in fact has mass dimensions. So your electrons again acquire masses proportional to this alpha because alpha is dimension 4. So it's very funny. You can study all of this, and fermions are ready to generate masses for themselves whenever the mass scale is available. That's eventually what we will study in QCD, how that mass scale gets generated, whether it is through lambda QCD, whether it is your gluon acquiring mass, does it acquire mass, does it not acquire mass, and eventually feeds into your quark propagator and into the observables that we will measure and predict in our last lecture we go to. But for tomorrow, what we will do is, first time, that you will say, you were saying that things will become very complicated. I haven't seen anything complicated. It's very simple, but we used a lot of approximations. We use the bare vertex. It's not the bare vertex. We eventually don't obey some of the gauge identities. Our coupling is not running. So hold on. We have to undo this and see if by undoing this, can we still make some reasonable answer to it? Are our results really robust under what kind of approximations we make to solve this or not, because we are not allowed to do perturbation theory anymore? That's what we will do tomorrow. We will see how many approximations we can undo and how still we can retain the solution. That will be the 4th lecture. And 5th lecture, we will generate the same thing for QCD with symmetry preservations and see how it is relevant for what is done here experimentally and how we can make predictions through this mass generation mechanism. Maybe I will make you overexcited, but Gustavo will not agree with me in some of the things I will say, is that this kind of truncations, when you do to QCD, not only tells you that you can generate mass, which is called chiral symmetry breaking or mass generation, just through the interactions, you see, but you have to have a large coupling where you have to solution which is not observed in perturbation theory. But not only this, but the structure of the propagator itself can also give you indication of confinement. But that is a bit tricky problem, and not everyone will agree with it. And even I am not completely sure of how eventually it would happen, because to observe to predict the observables that we see, even like form factors, we have to know this quark propagator not only along the real axis, but in the complex plane. Otherwise, we can't make the prediction. So the quark propagator also we have to solve when the momentum square is complex, not just real. And that tells us, when you see that, when you look at the propagator, many times you say the mass of the particle is where the pole of the propagator is, okay? But what happens is the pole of the propagator is in the complex plane, is not in the real axis. What we see sometimes is that whenever we find the pole of the propagator on the real axis, that particle is accessible in the laboratory. And it's a particle which can reach the detector. But when the poles move to the complex plane, then it's likely that it becomes a confined particle, not reaching the detector. That's where I stop.